In this video, we're going to go over section 8.1, and we're talking about sampling distribution. So, and the way that I'm going to do this one, I'm actually going to do it a little bit differently than before. I'm going to do the notes for 8.1, and then do the questions in the packet that correspond with 8.1. So specifically here, after I go over this portion, we'll do questions 1, 2, and 3. It's up to you if you want to write to follow along, but I also do have a key to the notes uploaded online. So if we're talking about a sampling distribution, talking about a sampling distribution, we're talking about the distribution of a sample statistic from all possible samples of a given size. So from all possible samples of a given size. And there's two different things that we're going to be working with in this chapter. We're going to talk about the distribution of sample means. So our sample statistic there will be the mean of each possible sample. And then we'll also look at the proportion. So that one's going to be the proportion of a sample that has a certain characteristic. So we can write that as a fraction, or we can write it as a percentage. So when we have a sampling distribution, again, we're taking all of the possible samples of a given size. So it could be pairs, it could be all samples of size 4, and then we're going to distribute all of the possible statistic samples. If we're looking for a distribution of either the sample mean or sample proportion, notice here that it's just going to be a specific type of sampling distribution. So we can see that our sample statistic in each of these, one would be the sample mean, and then the other would be the sample proportion. Since it's usually difficult to get information from an entire population, we usually have to estimate the true population values, and we've seen that before. So we're going to have a couple different new notations that come up in this chapter. We could talk about little n, which is the number in the sample. And we can have a capital N, which is the number in the population. And we've talked about that before, right? The benefit of sampling as a whole is to get a representative sample, so then we can kind of characterize the population. So it's not always feasible to get every single member of the population. So we just want to get some information to generalize out. What we could do is we could get what is called F bar. So it's an F with a horizontal line on top of it, and that is our sample mean. We're going to get that because we want to generalize out to get a value for our population mean. And that looks like a cursive M or a cursive U, and it is called mu. We also can get the statistic from our sample, that is little s, or our sample standard deviation. And then again, we would generalize that out to sigma, which is our population standard deviation. If this is hard to read, please again know that I do have a scanned completed copy, so that would be a little bit easier to read if you don't need to follow, or if you don't need to write it down. Lastly, we can have P, which is our sample proportion. So that would be a proportion or the fraction of people in our sample that have a certain characteristic. For example, if we had 30 people in our sample, for example, and we wanted to say maybe 12 of those 30 had blonde hair, then this would be our sample proportion. If we're talking about, this is P hat, by the way, so there's a little hat, little pointy hat on top of that P. We're talking about our population proportion. Then we would just have P without the hat. So again, the sample proportion is P hat, and then the population proportion is just P. I'm gonna erase what I have written here just to talk about the characteristic of both of these distributions. So if you were following along on the completed scanned copy, this is on the back of that first page. So we're talking about the characteristic. I guess it'd be nice to spell correctly, right? Characteristic of the distribution. And we're going to talk about the characteristics of the distribution of both the sample mean and the sample proportion. In both cases, the larger the sample size, the more closely that distribution will approximate a normal distribution. So as the sample size goes up, the distribution approaches normal. And the same thing applies here. So it doesn't matter which one we're talking about here. One thing that we can talk about though is what is called the best estimate. This is again for both of these. If we do not have our population information, again, our goal of taking that sample was to be able to describe the best we can the characteristics of that population. So we have to use what is called the best estimate value of our sample. The information we get from that, that's the best that we can describe that population. We can't do any better unless we take more samples. But we can say that the mean of the distribution of the sample means equals the population mean. And the same thing would apply for this sample proportion as well. So we would say the mean of the distribution of sample proportion equals the population proportion. And then in each case, we need to be able to calculate a standard deviation. So this is the same thing we've done before where we say, okay, we have a value and we're going to assume that this value is our best value that we can use to summarize information about the population. But we need to know if we're using that value, then a way to describe any value that falls within that range is going to have values of standard deviation. So the standard deviation of the distribution of sample means is calculated by sigma over the square root of n. So we're taking that population mean and then dividing it by the number in the sample. For our sample proportion, our standard deviation is calculated by taking the square root of p times 1 minus p over n. And notice that both of those standard deviation formulas are using the population value. And that is okay for now because we do know that the mean of the distribution equals either the proportion, sample proportion, and the population proportion, or the mean in the population mean. So it's okay to generalize out. I'm going to go ahead and scroll now to numbers 1, 2, and 3 in the problem. I'll start with 1 here. It says, among all of the 50,000 aspirin tablets produced by a pharmaceutical company over a given period, a sample of 200 tablets was tested, and it is found that 4% of them did not meet specifications. Identify the notation for each given number. So I'm going to go back through and I'm going to circle each value so I know that way that I include them all in my answer. And I need to identify the notation. So it says among all of the tablets produced, all of the 50,000. So I know that that would be the number in the population. So among all of them, that's our population is the 50,000. We then have a sample of 200. So little n here, the number in the sample is 200. So a sample of 200 tablets is tested, and it is found that 4% of them did not meet specifications. So we know that 4% of them, we're talking about 4% of the sample. The 4% is giving us a proportion. And we can see here that it's a sample proportion. So that's going to be p hat is equal to 4%. And a lot of times you'll see it, the sample proportion also denoted in decimal form. So either one of these would have been okay here, 4% or 0.04. Let's move on to number 2. Says the ages in years of the 4 U.S. presidents when they were assassinated in office are 56, 49, 58, and 46. Consider these 4 ages to be a population. So I'm going to underline that. Assuming that 2 of the ages are randomly selected to form samples of size 2 with replacement, find the mean of each of the 16 possible samples. So since we can have replacement, we're looking for how many different combinations can we have here. So if we're looking to pool 2 people, since we can have the replacement, we can pool 1 age, and then still, whenever we go back to form the second part of that sample, pool that same age again. So to find the mean of each of the 16 possible samples, we first have to list each of the 16 possible samples. So I'm going to just go ahead and go in order here. I can have 56 as the first part of one sample, and then I could, again, draw 56. I can have 56 and 49. So notice this one right here is possible because we have the with replacement. And we're just going to write all of the possible samples of size 2. So now I can have 56 and 58, 56 and 46. And then I can do the same thing with all of the other values. So now I can have 49 and 56, 49 and 49, 49 and 58. I think this is a different order than what I have on the key. but just know it's still the same sample. And 49 and 46. I'm not going to read out loud the last 8. So take a second and see if you can find them and then check your answer with mine. So those are all of the 16 possible samples that we can have. The question then asks us to find the mean of each of those samples. So I'm going to change my color here to make it a little bit easier to read. And what we're wanting to do is we're finding the mean of each of our pairs. So if I take 56 plus 56 and divide by 2, my mean here is 56. And I do the same thing in each pair. So the 56 and 49, if I add them up, divide by 2, I have 52.5. And I could keep going, right? 56, 58 gives us 57. 56 and 46, adding them together, dividing by 2 gives us 51. Again, just for not for you to get too tired of my voice here, I'll go ahead and just write the means out for the remaining samples, and then feel free to check your values with mine. So we have the mean of each of the 16 possible samples listed. Make sure when you have a question like this that we either circle it like I did on the completed key, or we use a different color like I did here in the video. Part B then asks, I'm gonna go back to the blue. Part B then asks, what is the mean of the sample means from part A? So now we're gonna take each of those values that was written in black. I'm not gonna write them all out here. We're taking all of those values. We're gonna add them all up. Since we're looking for the mean, it's the same as we would calculate before, right? Where you add all the values up, divide by our total numbers of values, or total number of values. So here we'd be dividing by 16. We end up getting a mean of the sample means value of 52.25. And then C goes on to ask, is the mean of the sample means equal to the mean of the population of 4 ages? So our mean of the sample means value, that's 52.25. We're asking, okay, well, is the mean of the sample means the same value as if I took everything in our population, so that 56 plus 49 plus 58 plus 46 divided by 4. So if I found the mean of my population, do I get that same value? And as it turns out, you do. You end up getting that 52.25. And it will always be the case that those two values are equal. I'm going to say yes, they're equal to each other, and yes, it will always be that case. So if we find all possible samples of a specific size and then calculate our mean of those samples, we will get the same as if we took everything in the population and found our mean. Go ahead and wait here. Let's look at number 3 here. So number 3 is going to bring back a concept that we've already worked with. So it's just to keep it fresh in your brain. It says a random sample of 64 newborn girls is obtained, and they have a mean birth weight of 3,390 grams. What is the probability? So we already know that we're gonna have to use something with our z-score table here, or at least we're assuming that we're gonna have to. What is the probability of randomly selecting another 64 newborn girls and getting a mean birth weight that is the same or more? And then it does it seem like this is unusual. We're given population information. So remember before, whenever we were taking random samples of a certain value, we were using that central limit theorem. So it said the more we take samples, the larger our samples are, the closer we're going to get to that normally distributed distribution that we would have if we took everything in that population. So I'm going to go ahead and look at the formula. Z is equal to, we're going to take whatever mean it's talking about here. So what value are we looking for them to have? We're looking for them to have a value of 3,390 or more. We're going to subtract mu, and then over the standard deviation. So over sigma over the square root of n. And remember, this comes into play whenever we were working with sample data. And just like we saw before, this entire denominator is that standard deviation. So we need to start substituting in the value that we know, the values that we know. A random sample has a random sample of 64. It has a mean birth weight of 3,390. We're wanting to know if we select another 64. So I know this will be 64 as my n. What is the probability that they have a mean birth weight of 3,390 or more? So this last sentence gives us the value of mu that we need. Remember that mu is which value again? So we should be thinking here it's our population mean. And then our value for sigma, for the population standard deviation, 706. Once we calculate, we should have a value of about 2.99. And remember that that is our z-score. So we are way over here. And we're looking for the probability of getting a z-score that is 2.99 or greater. So we need to figure out what is the probability of first getting this score smaller. And so we would go to that z-score table, and we end up seeing that the probability of getting a z-score of 2.99 or less is 0.9986. We want to be careful that we don't use that as our final answer, because we are looking for the probability of getting 2.99 or more. So now we're subtracting that 0.9986 from 1. I have a value here of 0.0014. If we want probability, you could leave it as that, but it's probably going to make more sense to turn this into a percent. That's a little floppy there. This is the probability of getting a z-score of 2.99 or a mean of 3,390 grams or more. The probability of that is less than less than 1%. It then asks, is this unusual? So we already know that since our z-score was 2.99 here, that it would be considered unusual. Because remember, it's anything that is greater than or more than 2 standard deviations away from the mean. So we can see it from this z-score here, or also this extremely low probability. So yes, it is unusual. I'm going to go ahead and stop this video just so we can prepare for the notes for 8.2, and our next video will go ahead and pick up right there.